a trip through the looking glass into autonomous learning investment strategies. Jeffrey Tarrant is the chairman and founder of MOV37. All opinions expressed by Jeff and podcast guests are solely their own opinions and do not reflect the opinion of any firm. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions. Clients of MOV37 may maintain positions in strategies and securities discussed in this podcast.
So, welcome to ALIS in Dataland. We're here at St. Catherine's College at Oxford University with a fellow here of Zubin Siganporia. And I just wanted to first ask Zubin, tell us a little bit about your background.
Sure, so I'm a mathematician. I actually studied at St. Catherine's as well when I was a student. And when I finished in 2011, I created a mathematical modelling data science consultancy, and we've been really lucky to work with some great people, some great groups in very diverse situations: genetics, law, security. I'm sure we'll talk about some of those things. And aside from mathematical modelling for industry, I still come back to Oxford every now and then. I'm a fellow lecturer, tutor here. And it's a real privilege to be able to teach some of the great students coming up and learn conversely from them as well. So that's what I do.
Wonderful. So just if we can kind of look at what's going on in the world of data hacks and things that are happening, GDPR. How do we know that with the threatening environment out there that we have security of data? And in general, you know, we've heard this terminology of homomorphic encryption and how it interrelates to the subject that I just asked about. What is homomorphic encryption and how can it be applied?
So I think a good way of thinking about it is, let's say you've got a cloud service, the Amazon cloud. Now, to make use of that, you might give a lot of your files, a lot of your data to this cloud. And usually that data is important to you. It might be medical data, it might be financial, whatever it is. So you don't usually want to give it to an untrusted entity like a cloud without encrypting it. Encryption just means that the other person can't see, right? So the issue with that in the traditional sense is fine. So the Amazon cloud can have all of this data encrypted. It can't see it, but it can't do anything useful with it other than return it to you because it's encrypted. It can't do anything. So the question is, can you encrypt it in such a way, give it to the cloud, and yet the cloud can still do something useful, can still process it usefully for you, and return an answer that's still encrypted, it can't see what it's doing, in a way that it's doing some of the heavy work, but it's still guaranteeing your privacy. So for example, you might upload loads of documents that are sensitive. Maybe you want it to return all the ones with machine learning in the title without it seeing machine learning or seeing the documents. And homomorphic encryption allows it to process that data without seeing what it is. And it was only within the last decade or so that it was even a theoretical possibility. Before that, we didn't know if this was possible at all. And I think a really interesting physical analogy that has come about by the person who first created a scheme. It was hopelessly impractical, but it was a proof of concept. And he came up with a physical example because this seems impossible. How can a cloud manipulate data usefully without being able to see what it's doing? It seems impossible. And he came up with this thought experiment that says, are you familiar with a glove box? So it's like a little box with two holes with gloves in it. So you can put your hands in these gloves and you can manipulate whatever's inside the box, but you can never get it out because it's within a locked, sealed box. But you can see it and you can manipulate it because you have gloves that allow you to reach through the gloves and touch what's inside. And he said, well, imagine someone gives you lots of gold and silver and they tell you to make this fancy necklace or whatever. Then you can still do it through the glove box. You can still usefully process it, even though you can't yourself get it out at the end.
Mm-hmm.
And the way that these systems usually works was you could do things up to a certain complexity. This is somewhat homomorphic encryption,
Right.
but you couldn't do arbitrary computations on that data. It's a bit like the gloves stiffening up after a minute, but it takes you 70 seconds to make your necklace. So the real interesting breakthrough was to say, well, you could take that box after you've manipulated it for a little bit, for a minute, and then put it into another locked box, which has a key, so you can use your gloves in the second locked box to unlock the first box and continue where you left off. So this is a way of transforming something that allows you to do complexity up to a certain level, but then extend it indefinitely, provided you have certain technical mathematical conditions. And so you can really do a lot of useful things. You can do large-scale analysis of DNA and people's genetics without them having to tell you what their personal medical data is. You can do that computation for everyone in the world, in theory, without anyone giving up privacy.
Mm-hmm.
And perhaps even more interestingly, you can ask the cloud to do things like return documents or whatever in such a way that the cloud doesn't even know that it's looking to return documents with these keywords. So not only is the data encrypted,
Right.
and it can't see what answer it's giving back, it can't even see what question it's answering.
Well, okay. That's interesting. So are there other forms of encryption that are anywhere near as sophisticated as that, or is this the way the world is going in the respect of how you just described it?
Well, this is one aspect of cryptography. There are loads, and they're all, I think, if you think about them at the cutting edge, they're all equally complex in some sense.
Right.
But perhaps homomorphic encryption, because it's becoming more interesting to more and more groups of people, and it's also becoming practical now. 10 years ago, 5 years ago, it may have been a theoretical possibility, but now it's actually almost becoming practical, and it's only going to become more practical. So I think a lot of research will go into this now as well. Yeah.
You use the term almost practical. So
Well,
what's next?
It's still a lot slower to do homomorphic encryption than it is to do just normal encryption, right? Where I can encrypt my documents, give it to the cloud in a standard way, and the cloud can return them. It can't do anything useful on it, but it's still so much faster to do it in those old-fashioned ways. This homomorphic encryption takes a lot of time to encrypt and to compute those functions. But when I say it's becoming practical, it's becoming faster and faster to the extent that people might actually begin to use this for simple applications.
Yeah. Interesting. So, so far as the blockchain is concerned, if we move to that side of things, and the threat that quantum computing could have of maybe making it less secure, so far as immutability of the data. Can you talk about that within the context of what we've just been discussing, or any other form of cryptography that's protecting the immutability of the blockchain?
Yeah, so classically cryptography is based on mathematical problems, fundamentally. And you find a difficult mathematical problem, and you try and create a system of encryption where to break that system of encryption is roughly equivalent to trying to break the underlying mathematical problem, which you've designed to be hard.
Right.
Now, in practice, it may be much more efficient to blackmail people or steal or whatever, but for the purpose of cryptography, it's founded on a mathematical problem. And classically, if you were to encrypt emails, one mathematical problem that is known to be hard is factoring large numbers. So if you take two really large prime numbers, you multiply them together, there's only one way of breaking that down into the two prime factors. And we're talking numbers that are bigger than a billion. We're talking hundreds of digits numbers, so really big numbers. And classical cryptography has been formed on the sorts of problems where to encrypt something, anyone can use this product of the two secret ingredients, whereas to decrypt, only I know these two secret ingredients and I can use that to go backwards and decrypt. And for immutability of data, and in blockchain, a big issue is not necessarily just the data on the chain, but also knowing that it came from me. So if I say Zubin pays Jeff £10, put that on the blockchain, we want to make sure that's really me saying it and not Jeff pretending to be Zubin saying Zubin pays Jeff £10.
Right.
So the way we do this is called a digital signature, by the way. I'm digitally signing my message.
Right.
And in exactly the way that these classical encryption decryption problems were based on things like factoring numbers, this problem of signing, digitally signing, is like me doing it in reverse. I do my two secret bits and anyone can check it was me because everyone can see the public product of these two prime numbers and check only I could possibly have written this message in this way, so it must have come from me.
Right.
So this is authenticity of messages. And quantum computing, people sometimes say quantum computers are more powerful than classical. It's not necessarily the power, it's just they fundamentally work in a different way. Mm-hmm. And you can exploit quantum physics to solve problems far faster than you can, certain problems, far faster than on a classical algorithm. Right. So this type of cryptography, factoring numbers, discrete logarithms is another popular one. It turns out there are good quantum methods of solving these problems, which puts all of this in jeopardy, the security. Right. So the question now is, can you come up with problems that even a quantum computer finds difficult? And that's some work that we've been doing recently. An interesting approach is to say, if I give you a large array of dots, I draw lots of dots on a piece of paper, and I put a random point on that piece of paper, what's the closest dot? Well, if they're arranged in some regular way, you can just look and you can see, and that's easy, right? But if I describe this pattern of dots in a very abstract, deliberately complicated way, and it's not just 2D, so you can visualize, but 100 dimensions, then this is actually, as far as we know, a difficult problem even for quantum algorithm. So you can come up with cryptography that is based on this problem, and that, as far as we know, would be secure even under quantum computers. So you can digitally sign messages and people can be confident that it really was from you, even when quantum attacks are exposed to it.
Okay, so this methodology of digital signatures, has it arrived yet, or is it being developed?
Absolutely no, it's arrived, and it's being heavily used in blockchain, for example, and lots of other things as well. When you sometimes you'll get an email and it will say this is signed by the other person, it really has come from them, and you can, if you really want, you can check their public information must have. The message they've sent must have come from someone with the two secret bits that went into it. So it definitely exists. And some groups have even been trying this, the post-quantum ways of doing it, just to see if it's possible. It's still a bit slower than the classical ways of doing it, but it's becoming practical now.
Right.
Yeah.
Well, great. So what sort of applications are you seeing? I mean, you're on our advisory board, and we're really lucky to have you, and you know how we're applying what we're doing in the area of investment management and things we've talked about before, but there are other industries that are out there, and I know you have direct experience in some of those other industries. Would you like to talk about that?
Yeah, sure. So I think finance is relatively unusual in the sense that people are very used to working in a quantitative type of way,
right?
Or at least they appreciate the power of being able to work in a quantitative way. So, for example, when we get asked to do financial products, it won't usually be, it might not just be predicting a certain value in the future. It may be a higher order thing. But can you predict the variance around that, or the risk associated with something, which you might take for granted, but other industries that aren't so used to working in a quantitative way don't even know what questions to ask in the first place. Mm-hmm. And so, yeah, you're right. We've worked with various groups. We worked quite a lot in sport at one point, where you're trying to design optimal training programs or strategy for, we work with some Olympic squads, gold medal winning squads, world champions. And the way that we try and approach these kind of less technologically driven groups is answering a simple question first that they may already know the answer to,
right.
but you're working with baby steps and showing, you know, my model is saying if the wind speed picks up to 5 meters per second, then this is the drop in performance that you're likely to see. And they'll say, oh yeah, well that's anecdotally exactly what we see, but we've never been able to explain it before, we've never understood why it's happened. And then you can say, yeah, and if you tinker with your technique in this particular way, you're likely to see a benefit of this. And then they'll say, oh yeah, that's exactly what we see. And that buys in confidence. And then you can say, right, so you really want to optimize your technique and your training to do this. And now, because they've already seen some simple applications of it, they're much more likely to believe the computer, which I think is still a psychological barrier for lots of groups.
It's kind of a mathematical crawl, walk, run, so to speak.
Yeah, exactly. Yeah, and we're working with lawyers at the moment. We're I mean, in essence, trying to revolutionize the legal world by making them actually take note of machine learning, artificial intelligence, and solving problems in a much more efficient way than they're doing just using humans. But again, you need to show them the crawl at the beginning. So, you know, just visualizing data is actually quite important to them. If they want to know who's interacting with who else within the firm or clients interacting with which groups, you could give a massive email spreadsheet of metadata, but you probably want to represent that graphically as some kind of network where people can understand. And when you show these are actually quite simple but very useful baby steps,
right,
which will immediately help the human, then you can lead on and say, right, now we can do natural language processing. Now we can automatically draft contracts for you. And they've already seen how it's useful, so they're more likely to believe it.
So that's starting with kind of a visualization.
Yeah.
Okay, cool. So you mentioned sports, you mentioned law. Is there anything else that you would like to talk about in applications? I mean, weren't you kind of working in the area of health and life sciences as well?
Yeah, so right, so we've had a couple of projects in health recently. So one is you often test medicine on animals, and the question is, how do you best convert that to humans so it's effective and compatible with a human? And this is quite a poorly understood problem. The way that human medicine or antibodies work is that you have a string of, they're called amino acids. Mathematically, they're just letters, one of 20 letters. And you put these 20 letters in a long string of length about 100. And they fold up in 3 dimensions. And they form a kind of 3-dimensional Y shape. And this latches onto a virus or a toxin, latches on, and it gets passed out the body. It's like a lock and key. And you can have slightly different sequences that will fold up in slightly different ways and will have a slightly different Y shape, and that will bind to a different toxin and take it out of the body. So there are a few problems, but one problem would be if you know the shape for a rat, an animal antibody, how can you find a sequence that will fold up for the human in a way that will be a similar kind of shape and latch onto similar kind of toxins? And we found there just isn't enough data to do huge neural network style machine learning approaches. But even with a few hundred data points, you can do things like a hidden Markov model, which is essentially you can probabilistically determine which regions of this string are most responsible for the shape. And you can target those bits, and then you can say, well, we know we've got a huge database of existing known human antibodies. Can we find the closest matches with these particular parts most important? So we really want to match these parts. We may not care quite so much about the less relevant parts. And this turns out to be effectively the state of the art now in designing human medicine based on what the animal antibody looked like. And there's another problem as well. So designing a bespoke shape for a particular toxin is quite an expensive, time-consuming process. So can you design about 1 billion in advance so that no matter what virus you come up with, one of those billion has a good chance of latching on? And this is a huge optimization problem. There are effectively an infinite number of possibilities. So 1 billion is actually a really small number here. And can you find the most diverse set of 1 billion shapes possible and work out what strings would fold into those shapes in order to target the widest variety of toxins to humans possible? So we did that as well. And I think that also highlights the importance of having fast algorithms, because you can't, even if you can very quickly roughly determine a shape, to do this billions of times and work out the billion optimal set of things that will work, you need to be able to work really, really, really quickly in order to do this huge optimization problem.
Sounds like a lot of math, a lot of calculations.
There is.
So, yeah. But if you end up, as you say, with 1 billion, I guess kind of like solutions to a problem.
Yeah.
So it's kind of like a library that you have.
Exactly.
And it's almost like you could pull a book off the shelf and say, this one applies to this.
Exactly. That's exactly how to think of it. Yeah.
Right.
Yeah.
So who owns the library?
The company that we designed it for and us. Yeah. We designed it in collaboration with them, and they, and I guess we, but they're the experts in manufacturing these things from the ground up, and they have the library.
Yeah, but you're a mathematician,
Yep.
right? And so you're talking about all these different domains you're going into.
Yeah.
Sports,
Yeah.
health.
Yeah.
And how do you really get the domain knowledge to parachute in and find these solutions, whatever they are?
Yeah. So I think well, firstly, more and more problems are really fundamentally a data problem. And you just need enough domain knowledge to understand the problem in many instances. And it helps to work with, and we're very, very lucky, we work with some really great groups of people, geneticists, who take the time to explain it. They take a day out to explain what's going on in a way that we understand enough to have a go at the problem. And then, as long as you can model it mathematically, or even just throw enough data at it to find a pattern, then you can approach it in a very mathematical way. So a good example, a topical example, is in language translation, where it's now very well known that neural networks, you can throw lots of data, you can say these are loads of French sentences, here's the English translation.
Right.
And the machine learning approach will just be able to pick out the patterns in order to do translation. Now, you don't, as a mathematician, need to understand how to translate from French to English. You just need enough data to find the patterns in this structure.
Okay.
Now, you need experts at the beginning to create these large databases or to explain the problem in enough detail that you understand what you're trying to solve. But ultimately, you can abstract it nearly, well, maybe not nearly everything, but a huge amount of problems down to something that can be attacked in a very mathematical way. To design a program that beats every human at Go or chess, it's enough now actually just to know the rules. You don't need to be a grandmaster to design a system that plays as well as a grandmaster. You just need to see enough examples of games to pick out those patterns and play against yourself. That's the AlphaGo Zero approach, and you can beat the best domain experts in the world.
Yeah. Well, good. I don't know if you noticed, but we're on Oxford campus and the bells were ringing.
Yeah.
It's 7 p.m. here, but I think it chimed like 500 times. So
yeah, these are
I don't
the
know.
Oxford
Is there a
bells.
mathematical model around that?
No, this is just a Oxford. So you say 7 o'clock. It's. I think they're designed to ring at exactly 7:05.
You're right.
It's
It's exactly 7:05.
It's they're called, I think Christchurch time is 6:07 rather than 5 or something weird. But this is just a tradition calling people to dinner in 10 minutes time.
Oh,
roughly,
okay.
yeah.
Which
So
we're
we've
going to
got
go.
Yeah.
So we better speed up the process here. So yeah, but I think you adequately explained that it's not necessary to really have the deep domain knowledge because it's just a relationship which you're trying to find, which is a mathematical relationship.
Yeah, exactly, yeah.
So can I ask the question of, you're here at Oxford, you have some of the brightest students on the planet, or at least in England. Or I actually I met some Asian students here today. Yeah. It was really interesting. You're there as their fellow, instructing them, but how much of this is a dynamic back and forth of learning actually back from your students as well, right?
Yeah, I think, well, you're right. A lot of them are really brilliant mathematicians in their own right. And I think it's quite interesting when you may have a bit more experience than them as you're teaching and you've seen the problems before, but seeing how they approach certain problems is a quite interesting thing from the other side. And even asking, so I had 2 people in here for a tutorial earlier, both at the very top of Oxford, both of whom revise in completely different ways. One might write down a proof 10 times and just memorize it, whereas the other might try and work out a few tricks in the middle and then back themselves to work out the proof in exam conditions. And so everyone has very, very different approaches to learning, and they can be very effective. One thing that I think is the common thread is that people like to think mathematical geniuses are born, or you're born with a mathematical talent, and I don't think that's true at all. But you can work maybe to a limited extent, but hard work gets you very, very far. And almost all the time, the people who work the hardest and are prepared for a lot of suffering, because maths is often you can't prove something. It's very rare that you have that insight, but then it makes it all worthwhile, your hour of struggle before. But the people who do work those longer hours and pursue it tend to do really, really well. And then later on, it's a bit like chess grandmasters. Some moves seem intuitive and you think, wow, they're just born with this gift. It's just because you've seen the pattern so many times, even if it's subconsciously, that you just see these kind of tricks more and more often. You have a feel for what will work because you've just done it so many times. And I think being on the other side, seeing them get to grips with this pattern recognition and seeing how they approach things differently in 3rd and 4th year relative to 1st year it's quite an interesting experience for me. And you do get to learn from them as well.
So hard work does pay off.
Yeah,
so
definitely.
And it's kind of like what Linus Torvalds says about who invented Linux, right?
Yeah.
And he says everyone has a great idea, but it's just hard work of engineering, implementing and executing.
Yeah, right. And I think having a team of people, it can work sometimes where some person has brilliant ideas, but then they are often not the person to code them up over the next year, because they're just interested in coming up with these great ideas and then moving on to the next great problem, trying to have a go at that. And you need all types of people where, some people are just prepared to take other people's great ideas. They're very smart people and just get them to work. And this collaboration between different people in the team is crucial, I think. You need good interaction between them. And I run some student projects, and it's great to see how some people come up with ideas, other people code them. There's great interaction. At my company, I'm lucky enough to work with my cousin, who's really brilliant. He does more of the computing side. One of the professors that I was lucky enough to have when I was a student was really the one who encouraged me to set up a company in the first place, and is a complete genius, and I don't use that phrase lightly at all, but works in a very, very different way to me, and we got along incredibly well, but work in very different ways, and I think sometimes that can really benefit the team as well.
Yeah, wonderful. So I know we're going to have to head off to the dinner.
Yeah.
The bell's ringing.
Yeah.
So hey, Is there anyone of any kind of creative type that has influenced or inspired you, and in any particular area? And this is a wide open question. Creativity.
Yeah. So actually, the person who I just mentioned, so Philip Bond, who he's a professor of I don't know how many things now, but maths, computing, probably physics at some point, engineering. I think he's the only professor of creativity in this country now, or chair of creativity.
Professor of creativity
in Manchester, I believe.
Wow.
I worked very closely with him for the first few years of having my company, and lucky enough still to interact quite a lot with him. And quite often when we were working together, in a nice way, I saw some of his code, we talked about things, and it never appeared hugely complicated. But I think there is a lot of skill involved in being able to see a key idea and simplify it enough because you really understand it. And he's one of those types of people that just tries to solve problems in a different way to other people. Because if other people have tried for years on certain approaches, you probably need another approach anyway. The standard approaches don't tend to work. And building things from the ground up in very different ways. So for example, just getting code to run 1 million times faster than anyone else has done by really stripping down the core idea and writing it completely from scratch and then adding complexity later, rather than going in reverse and trying to build a model that does everything and then trying to make it fast, which almost never works.
Right.
So he approaches problems in a different kind of way to most people, I think. And I was lucky enough at the beginning to be exposed to that way of thinking quite a lot. And
that's interesting because as an American, we have Richard Feynman, who had a very similar philosophy, right?
Right, yeah.
And actually, he had the philosophy as well, is that if you try to complicate things and create your own vernacular, so to speak, it confuses the simplicity that you're trying to achieve.
And you're right. And I think if you really deeply understand something, quite often you can explain it to a 10-year-old or whatever, because you understand the complexity enough to remove it when you're talking. And some things are complicated, but if you understand them deeply enough, you can abstract them away in a way to explain it to anyone.
Which is exactly what you did when I asked you about homomorphic encryption. And thank you for that. But and also, just thank you for participating in this, Zubin. And it's been a delight to have you on our advisory board. And I truly appreciate you participating in ALIS in Dataland.
No, and likewise, it's a real privilege to get to work with you and the other advisory board members. So thank you.
Okay.
Great.
Cheers.
Thank you.
Thank you for listening to ALIS in Dataland. For show notes and more information on ALIS and MOV37, please visit our website at www.mov37.com.